This is CS50, Harvard University's introduction to the intellectual enterprises of computer science and the art of programming. My name is David Malin, and if you are among those in the room who are thinking, why am I in a class of computer science, realize that I, too, felt that exact same way. In fact, my freshman year, I didn't quite get up the nerve to take this class or computer science more generally, and that was largely because I was intimidated by it. I was a little nervous. It felt well out of my comfort zone, and I really didn't know at the end of the day what it actually was. But realize if you too were feeling a little bit of that, or even if you're among those more comfortable who have dabbled in computer science or programming, realize that there's so many blanks that we can fill in along the way, so that ultimately at the end of the semester, everyone will feel themselves on the same page. And until then, rest assured that 68% of the people sitting to your left and to your right and behind and in front have never taken a CS course before, which may very well be the demographic into which you fit. But realize, too, that with such an amazing support structure, with so many office hours and sections and materials and beyond, realize that what's ultimately important in this course is not so much where you end up relative to your classmates in week 10, our final week, but where you end up relative to yourself in week 0. And indeed, that is where we now are. And as it turns out, computer scientists start counting at 0. And so over the next 11 weeks, will we take you from being among those less comfortable, or perhaps somewhere in between less comfortable and more, to feeling much more comfortable and confident and capable than that. But to get there, we need to understand what computer science really is. And this was something I didn't understand until I set foot in a room like this. And I dare say we can distill computer science into just this picture. Computer science is about problem solving. And I know that high school courses typically do kind of paint a misleading picture that it's only about, and it's entirely about programming and people with their heads down in the computer lab working fairly antisocially on code. But the reality is it's all about solving problems, and very often solving problems collaboratively, either in person or by leveraging code, programs that others have written in the past. And what does it mean to solve a problem? Well, you need inputs. So there's a problem you're trying to solve. That is the input. And you want output. You want the solution to that problem. And the sort of secret sauce of computer science is going to be everything in this proverbial black box in the middle, that over the next several weeks, will you begin to understand exactly what you can do with that. But in order to start solving problems, we kind of just need to decide as a group like how we're going to represent these problems. And what might a problem be? Well, in this room, there's a whole bunch of people. If we wanted to take attendance or count the number of people in this room, I might need to start keeping track of how many people I see. But how do I represent the number of people I see? Well, I can do it sort of old school, and I can just take out a piece of chalk or whatnot and say, all right, I see 1, 2, 3, 4, 5. I can do little stylistic conventions like that to save space or remind myself 6, 7, 8, 9, 10, and so forth. Or I can, of course, just do that on my own hand. So 1, 2, 3, 4, 5, and so forth. But obviously, how high can I count on just one hand? So 5, you would think, but that's just because we haven't really thought hard enough about this problem. It turns out that with just these 5 fingers, let alone these 5 more, I can actually count rather higher. Because after all, the system I'm using of hash marks on the board, or just now with my fingers, is just kind of keeping my fingers down or putting them up to represent ones, really. But what if I actually took into account the order of my fingers and sort of permuted them, so to speak, so that it's really patterns of fingers that represent the number of people in the room, and not just the mere presence of a finger going up or down? In other words, this can remain 0. This could still be 1. But what if 2 is not just this, the obvious, but what if it's just this? So raising just 1, my second finger. What if then 3 is this? So we have 0, 1, 2, 3. That's going to lead us to 4, somewhat offensively. But if we then jump ahead to 5, I might now permute this finger and this finger up. And if I want to now represent 6, I could do this. And now 7. In other words, I've expressed so many more patterns on my hand already. And if we keep doing this, I think I can actually represent, painfully perhaps, like 32 different patterns, and therefore 32 different people on my hands alone, or 31 people if I start counting at 0. So, but what is that? What's the relationship, and how did we even get here? Well, it turns out that computers are kind of simplistic, much like our hands here. At the end of the day, your computer is plugged into the wall, or it's got a battery, so it's either has or it does not have electricity. At the end of the day, that is the physical resource that drives these things in our phones and all of technology today. So if there's either electricity or not, that kind of maps nicely to no finger or yes finger. And indeed, computers, as you probably know, only speak what language, what alphabet, so to speak? Yeah, binary. Bi meaning 2. And indeed, that refers to the fact that in binary, in computers, you only have 2 digits, 0 and 1. We humans, of course, have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we can combine those to count even higher. But computers only have 0, 1, and then that's it. Because at the end of the day, there's actually a direct mapping between power being off and it being a 0, or power being on and it being 1, or some electrons or whatever flowing from your battery or from the wall. So this is why computers tend to speak only binary, because at the end of the day, it just maps really cleanly to what it is that's powering them in the first place. But how is this actually useful? If computers only have zeros and ones, how can they do anything useful? Well, think about our human world, where you might have this pattern of symbols. This is decimal, dec meaning 10, because you have 0 through 9. And this is, of course, 123. But why? If you haven't thought about this in quite some time, this is really just a pattern of 3 symbols, 1 and 2 and 3, shapes or glyphs on the screen. But we humans, ever since grade school, have started ascribing meaning to each of these numbers, right? If you think back, this is the ones column, this is the tens column, this is the hundreds column, and so forth. And we could keep going. And so why does this pattern 1, 2, 3 mean 123? Well, it's because all of us sort of intuitively nowadays are just quickly in our head doing 100 times 1 plus 10 times 2 plus 1 times 3, which of course gives us 100 plus 20 plus 3, and then the number we know mathematically as 123. But we're all doing this so quickly, you don't really think about this anymore. Well, computers work fundamentally the same way. They don't have as many digits, 0 through 9, as we do. They only have zeros and ones. And so if they were to store values, you're only going to see zeros and ones on the screen. But those zeros and ones just mean different things. Instead of having a ones place, tens, a hundreds, they're going to have a ones place, a twos place, a fours place, and then 8s and 16 and beyond. Now, why? Well, 1 and 10 and 100, turns out those are powers of 10. 10 to the 0 is technically 1. 10 to the 1 is just 10. 10 to the 2 is 100. And that's why you have ones, tens, hundreds, thousands, and so forth. Computers are apparently using powers of 2. Not surprising, binary 2. So if you only have ones, twos, and fours as your placeholders, if a computer were storing these digits, 0, 0, 0, that computer is presumably storing what number so far as we humans understand it? Well, that's how a computer would store 0. If a computer is storing literally 0, 0, 0, just like in our human world, that also is 0. But that's technically because it's 4 times 0 plus 2 times 0 plus 1 times 0, which is obviously 0. Meanwhile, if a computer is actually storing not just, say, 0, 0, 0, but instead is storing this value in binary, what does that map to in decimal? So that's 1. And now why, if we change this 0 and 1 to this value here, is this 2? Well, mathematically for the exact same reasons. And so earlier I had 5 fingers, but if you consider just my first 3, when I did this, holding up one finger, I was representing 2. And if I want to represent 3, recall that I put up this second finger. And so the reason that could nicely represent 3 is because all I was doing with my human hand was counting in binary. And I could keep counting more and more and more. And so if I have 5 fingers, or 5 bits, bit meaning binary digit, I could count up, it turns out if we do the math, as high as 31 by starting to 0. It's going to be hard to physically do that, but we could. So why is this useful? Well, at the end of the day, a computer, therefore, can represent any number of values, from 0 to 1 to 2 to 3 to some number much, much, much higher than that. All it needs is enough bits, enough zeros and ones. Well, what are those bits? Well, all of us have these days in our phones sources of light, for instance. So I could actually say that this physical device right now might be a little hard to tell. It does have a flashlight, and it's technically off at the moment. But if I turn this flashlight on, thereby using some of the electricity, then now I'm storing a 1. And so the phone is on. Now it's off. Now it's on. And if I see, can I borrow someone's phone real quick? May I? OK. And flashlight. How do I turn on the flashlight? Oh, shake it. That's OK. OK, thank you. That's OK. Oh, thank you. OK. So this is great. Now I can count higher. So now now this represents the number what? If I have 2 light bulbs or 2 switches on at the moment. Yeah, 3, because I have a 1, and I have a 2, which of course is going to end up equaling 3. And if I pick up a third phone somehow, I could count even higher. Technically, if I had 3 light bulbs on, 1, 1, 1, what would that value be? 7, because it's a 4 plus a 2 plus a 1, and so forth. Thank you so much for the spontaneity. So why does this not lead to limitations for us? I can count in decimal as high as I want. I can now count in binary as high as I want, so long as I have enough bits. But how do I actually represent other information? Well, if I want to represent something like a letter, how do I get there? If computers only have electricity in them, and they use binary to count, and yet somehow they're much more useful than just doing math. They can have text messages and emails and websites and videos and more. How do we get from zeros and ones to letters? Well, yeah. Sorry, a little louder? Yeah, we just need to kind of relate the numbers to letters. In other words, all the people in this room just need to decide at some point that, you know what, if we want to represent something like the capital letter A, we just need to decide on a pattern of bits, a pattern of fingers that's going to represent A. And it turns out humans years ago just unilaterally decided 65 shall be the decimal number that represents capital letter A. And you might guess capital B is represented by what decimal number? 66, and then C is 67, and so forth. And there's a mapping of like 128 or even 256 possible values for all the keys you might see on a typical keyboard in order to represent letters. Now, how does a computer distinguish, though, numbers from letters? Well, it just depends on the context. If you're using like a calculator program on your Mac or PC or iPhone or Android, well, the computer, the device, is just going to know contextually, let me interpret this pattern of zeros and ones as actual numbers to do math. But if you're using the SMS app or the Messages app on your phone, you're going to actually be in the context of text. And so your phone is going to interpret that same pattern of zeros and ones, or light bulbs being off, or at the end of the day, transistors, tiny pieces of hardware in computers that are either on or off. It's going to interpret those patterns as just representing a letter if you're in the context of a text messaging application or Microsoft Word or Google Docs or the like. It completely depends on context. The system we humans came up with, just called ASCII, American Standard Code for Information Interchange. The name isn't interesting, but the fact that we all agreed years ago that 65 is A and so forth is what's important. And so, for instance, if we look at this mapping here of just the first few letters, what does this mean? If I were to now get a text message, and I had the ability somehow to look underneath the hood, so to speak, at the pattern of zeros and ones that someone had just texted me. And that pattern, if I convert it to decimal, technically said, let's say 72 and 73. So I get a whole bunch of zeros and ones. I do some math, and I realize, OK, I just received 72 and 73. But this is texting, and so it's not just numbers my friend is sending me. It's a message. What message did my friend likely send me if he or she sent 72 and then 73? Yeah, hi, HI, because if you skim ahead at the right there, that just happens to be in ASCII the mapping between 72 and 73 to H and I. If technically the message had a third byte, if you will, a byte, if you've ever wondered, it's just 8 bits. It's convenient to talk not in terms of single bits, where you can't count very high, but with a byte or 8 bits, you can count higher. And so it turns out if I received a third byte, another sequence of 8 zeros and ones together, 33, how would we know what this message now is? Yeah, so it turns out you would not know this other than by guessing or Googling or just coming in with this knowledge. This is now hi with an exclamation point, because 33 just so happens, if you look it up, to map to an exclamation point as well. Now, if we actually looked at the binary of this, you would actually see this pattern of zeros and ones. This is how you represent 72 in binary. This is how you represent 73. And this is how you represent 33. And notice I've only used 1, 2, 3, 4, 5, 6 bits, even though I technically tend to receive things in units of 8, units of bytes. But why did I not bother writing another 0, 0 here and another 0 here? Does it matter when you write these things out? No, not really. Like in English, in our human world, if you were to write 1, 2, 3, that's 123. If you were to write 0, 1, 2, 3, that's still 123. So even though we tend to get them in clusters of 8, we don't necessarily need to write those when just talking about them. So what have we done? Well, let me introduce a fancier word now known as abstraction. Abstraction is just a term generally used in computer science, and we'll soon see in programming, for taking some low-level, like literally low-level implementation details, like minutia even, and understanding them at some point, but then deciding this is not a useful level conceptually to think about problems. I really don't want to solve problems in this world thinking in zeros and ones. I'd much rather think about things minimally in decimal, or better yet, in the context of letters if I'm actually receiving text, or even some other representation. So abstraction is about taking fairly low-level details and just simplifying them so that we can have a more useful conversation and never again worry about where where the electricity is coming from, we can just stipulate my computer can represent zeros and ones, therefore it can represent numbers, therefore it can also represent ASCII or letters, and we can kind of move on and start solving more interesting problems. But it would seem that we can't solve all problems because on my keyboard here, this American keyboard here, there's a whole bunch of symbols, like 100 or 2 maybe in total, if we actually hit Shift and Option and all that. But what you don't see are some pretty common characters, especially in a very international audience. What can I apparently not even type on this keyboard? What kinds of symbols? Yeah? Anything with an accent, if you have accents over vowels or other letters. What else? I'm sorry? Umlauts or other characters above letters? Yeah. Pound, like pound symbol? Oh, like the UK pound symbol? Sure, in other countries too. Any number of Asian languages. There's so many symbols that are not depicted on this keyboard. And yet somehow, all of us with international keyboards or phones can surely express themselves. But that's because phones and computers these days don't just use ASCII. ASCII literally use just 8 bits total. Technically 7, but then ultimately really 8. And with 8 bits, if you actually do the math, if you have 8 bits or 8 fingers, you can only permute them in 256 total possible ways, which is to say that you can only represent 256 characters using ASCII with numbers underneath the hood, and that's not enough to represent so many different symbols like those enumerated here. You can't represent any of the accents that you can nonetheless type on your Macs and PCs, and you certainly can't type these things, which are very much in vogue, which even though they're pictures, they're actually just characters. Because it turns out some years ago, the world decided 8 bits is not enough. Let's start using something called Unicode, where you actually use 1 or 2 or 3 or even 4 bytes. So 8 bits or 16 bits, 24 bits, or even 32 bits to represent characters. And now we have the ability to represent thousands or even millions of characters. And frankly, dare say, the result of that huge amount of availability is partly why there are so many of these things these days. And they just keep making more because there's just so many different numbers available to us. So Unicode is often a specific version of it called UTF-8, which we'll see before long. But let me ask this question here. This is a crying face with joy, I think this is called. So it turns out, according to Apple or iOS, this is the most popular emoji that at least iPhone people are sending to each other. So when you're receiving this, though, if we can really take the fun out of this, what pattern of bits are you actually receiving from your friend? He or she is clearly trying to express some emotion, but really what your friend is sending you the decimal number 128,514. Or really, if you looked at the zeros and ones coming to you over the internet or airwaves, you're getting this pattern of zeros and ones, which is hardly joyful or hardly descriptive. But all your phone or computer are doing is seeing this pattern of bits, looking it up in like a little cheat sheet and saying, oh, whenever I see this pattern of bits in the context of text, like texting, I should actually display it as that picture. Now, that picture has a lot of yellow and other colors in it, but how do we even get there? Well, it turns out that this same pattern of numbers, 72, 73, 33, which just to be sure, a moment ago meant what? Hi. In the context of a textual program like Microsoft Word, Google Docs, texting, this means hi. But what if you saw this same pattern of bytes? And again, we could draw the zeros and ones, but it's not interesting anymore. So we're going to abstract away at the decimal level. If you got this same pattern of zeros and ones or numbers in the context of like Photoshop or a browser or some kind of photo program, well, it might make more sense to interpret it not as text, but as imagery, some kind of colors. Well, it turns out there's this other system in the world, and you might have seen this acronym before, called RGB, red, green, blue. And this is just a way of humans having standardized years ago that, you know what, if we want to represent a dot on someone's screen, otherwise known as a pixel, tiny little square on the screen of your phone, your laptop, or even TV these days, we're going to use 3 bytes. 1 byte to specify how much red should be in that specific pixel. 1 more byte to specify how much green should be combined with red to form that pixel. And then 1 more byte, a third, to represent how much blue to combine with those other 2 colors to make a new color altogether. So it's kind of like combining paints, except in this case, it's more really waves of light in order to get a specific color using just red, green, and blue as your palette. And so if we were to see this red, green, blue pattern and say, you know what, give me 72 red, 73 of green, and 33 of blue, if the total possible range, as I alluded to earlier, is like 0 to 256, or technically 0 to 255 if you start counting in computer science like from 0. This is like a medium amount of red, medium amount of green, and just a little bit of blue if the range goes from 0 to 255. So if you combine these three things together, anyone know what color you get? Yeah, so it's kind of a light yellow that looks like this. So if a computer is storing a single dot on the screen that happens to be in yellow, what the computer is actually storing is not this dot physically, but a pattern of 3 bytes. How much red, how much green, how much blue should the computer display at this particular point? So if we look at this crying face of joy, and we kind of enhance or zoom in on it here, you can actually see it start to pixelate, so to speak, where you start to see the dots. If I punch in a little more, now you can really start to see the dots on the screen. And if I go in even farther, you can actually see the tiny little squares that compose this image, most of which at this zoom level are yellow, but a bunch of which are black, a bunch of which are like light black or dark yellow. And that's what composes this image ultimately. So this is to say, if you count up all of the pixels on the screen and then multiply it by 1, 2, 3 bytes, that's how many bytes or kilobytes or megabytes, if you've heard those terms, are going to be stored on your computer just to represent that image. So we've gone from electricity to down here, so to speak, to zeros and ones, to decimal, now to colors. Well, with colors, you can get images. What comes after images? Well, we've all watched videos or movies, certainly digitally these days. Well, what is a movie or a video file? How might that be implemented? Say a little louder? Yeah, it's a collection of images. If you've ever heard of frames per second, like movies tend to be 24 frames per second or 30 frames per second, that just means that a typical movie, every second is showing you 24 or 30 images per second, and they're just flying by so quickly that you actually don't notice you're just watching a sequence of static images. It's like as a kid, if you ever had one of those paper flip books where there's tons of drawings in them, and as you flip through the pages, you see things moving, but that's just because your eyes are just seeing little snapshots ever so quickly of something moving on the paper. That's all a video file actually is. So if you have an iPhone and you've ever played with these animojis, so to speak, well, all those are little video files composed of lots and lots and lots of images that you have saved on your phone or texted to someone else. And if we just think now, OK, now we're at the point of video, but that's OK. Videos are just bunches of images. Images are just bunches of colors. Colors are just patterns of bits. And bits, at the end of the day, are just the result of electricity coming into my machine or transistors turning switches on and off. Like, we've all of a sudden told like this entire story, but none of us ever is going to need to really think about binary in the context of videos, because a video is just an abstraction on top of bunches of images. And images are just an abstraction atop bunches of pixels, and so forth. So we can keep painting this hierarchy that just allows us to talk about things at a more useful level. And the reason we had this conversation is just because we needed a way to represent inputs and outputs to problems. So let me pause there for just a second to see if there's any questions. Anything at all? No? All right, so what's inside this black box? Well, it turns out this is where the really interesting work starts to happen and the thought starts to come in. This is the proverbial algorithms, step-by-step instructions for solving some problem. And some of you might have solved this problem before, either digitally or textually. But of course, if you have like contacts in your phone these days and you've got bunches of friends and family, odds are they're alphabetized by first name or last name. And you have autocomplete these days. But it really is just a long list of names and numbers. That's not all that different from yesteryear's implementation of the same problem, which was this device here, a phone book. Now, this phone book might have a friend of ours in it, say Mike Smith, whose last name starts with S. And I could, of course, if trying to find Mike Smith, start by looking at the first page, the second page, the third page, the fourth page, and eventually just hopefully find Mike Smith. Indeed, is this algorithm, this step-by-step process, correct for finding someone like Mike Smith? Yeah, it's correct. It's stupid and slow, perhaps, because it's going to take forever in a phone book of this size. But it is correct, because if Mike's in here, I will, in fact, find him. But I could do this better. I could do it sort of 2 at a time. So 2, 4, 6, 8, 10, so imperfectly, 10, 12, 14. Is that faster? Obviously, it's going twice as fast. Is it correct? No, why is it not correct? Yeah, I might miss him, right? Mike just accidentally might eventually get sandwiched between two pages, and I have the unlucky experience of just missing him. Now, is it fixable? Yeah. I can probably, once I hit like SN or the T section, for instance, I can just say, all right, obviously I've gone too far for Mike. Let me just double back one or just a few pages. So it is fixable. And so long as I've saved time by flying through this twice as fast, can I at least afford to spend a few more steps at the very end just to find Mike Smith. But none of us are going to do that. And our Apple devices and Android devices certainly don't do that for efficiency today. Odds are most of us are going to do what to find someone in any book like this? Yeah, open to, roughly the middle, or maybe bias ourselves toward the end because S is after the middle. But, I'm in the middle of the phone book here. And now if I know that Mike is in the S's and therefore over here, where do I know he's not? He's not in the beginning, and I can literally tear a problem like this in half, throw figuratively and literally half of the problem away, and be left with fundamentally the same problem, but it's half as big. I went from like whatever, 1,000 pages to 500 pages, and I can now repeat this algorithm. I look down, I'm a little too far. I'm in the T section now. OK, I can again tear the problem in half, throw that half away, taking a 500-page byte out, a 250-page byte out, now leaving myself with just 250 pages more. And notice just how quickly I got here. The first two algorithms got me from 1,000 to 999 to 998, or 1,000 to 998 to 996. But here I went from 1,000 to 500 to 250. Feels like we're making up time here. And indeed, if I keep repeating this process, hopefully I'll be left with just one page of the book that Mike is either on or not, at which point I will call him. And so that's an algorithm that honestly leverages probably all the intuition we have. And a lot of what programming is going to be is thinking about a problem like this, figuring out how to divide and conquer it, and then expressing yourself in a way that the computer can then solve that problem for you. And just to paint a picture of how much better this algorithm is, well, if this is just a very abstract chart where we have on the vertical or y-axis how much time it takes to solve a problem, and on the horizontal axis how big the problem is. So the farther out you go this way, the more pages in the problem, the more pages in the phone book, and the higher you go up here, the more seconds or page turns it's going to take. That first algorithm is just like a linear slope, so to speak, because for every additional page in the book, it might take me one more second, right, up, right, up. It's just a one-for-one relationship with pages. The second algorithm, if I plot it, where I'm flying through twice as fast, what is that line going to look like instead? Yeah, it's going to look lower than this one. It's still going to be a straight line because now there's a 2-to-1 relationship. But if you've got a phone book that's got this many pages, and in the first algorithm it took this long here, well, in the second algorithm it's going to take it will take half as many steps, plus or minus 1 or 2 if you need to actually double back a little bit. But that third algorithm is what we'll call logarithmic. If n is the number of pages in the phone book, the first algorithm in the very worst case might take all n pages to find Mike Smith. The second algorithm is going to take half as many steps because I'm flying through it 2 at a time. But the third algorithm is going to look and feel like this. It's going to be curved and ever so slowly rising and rising and rising. The implication of which is if Verizon or the phone company doubles the number of pages in the phone book next year because Cambridge and Somerville merged together in the phone book, and we now have 2,000 pages. Well, how many more steps does my third algorithm take? Just one, because I can take a 1,000-page byte out of the problem with that clever algorithm, whereas my first two algorithms would take it 1 or just 2 pages at a time. So that is to say, we have to hugely increase the size of this problem just for the number of seconds or page turns to appreciably actually increase. And so as we start to learn about programming, it's again going to be leveraging of this intuition in order to actually solve problems in code more effectively than we might without code alone, without that intuition alone. So let's formalize this now. So that was kind of a very intuitive way of dividing and conquering a problem. Just kind of made sense to go in the middle, tear it, then go to the other half or the other half and tear it again and so forth. But a computer, even as cool as Alexa and Google Home and all this are, you can't really just talk to them as another human and have them execute things correctly. I struggle just to get Siri to like set a timer on my phone. So we're not quite there yet. So we're still at the age where we have to be ever so precise with computers, voice activated or otherwise, and so thus enter pseudocode for now. Pseudocode has no formal definition. This is just a way of saying use English-like syntax or any spoken language and just express yourself succinctly and correctly so that a computer or a robot or even another person can understand what it is you're trying to say. So here, I propose is an algorithm written in pseudocode, English-like syntax, that just gets my point across. And I could write this in any number of ways. I've numbered the steps from 0 on up just for the sake of discussion, but this would seem to capture what I did there. Pick up the phone book, open to the middle of the phone book, look at the names. If Smith is among the names, call Mike. Else, if Smith is earlier in the book, go to the left, specifically the middle of the left half of the book, and then go back to step 2. Because indeed, I was just doing the same thing again and again. And the reason I wasn't doing it forever was because every time I repeated myself by opening and tearing, I was shrinking the problem. And I can only shrink a problem of some fixed finite size so many times until I get just one page. And so if I can continue this logic looking to the right or to the left or just quitting, if I don't find Mike at all on the last page, this would seem to capture more precisely that code. Well, let's actually excerpt from this now a few concepts and then start to apply them to actual code. Highlighted in yellow here, I dare say, are all of the verbs or actions. These are the functions, as we're going to start calling them, in this algorithm. A function is just a specific step, a specific action you take in order to do something. And so in yellow here, pick up, open to, look at, call, open, quit, are all actions or verbs, or henceforth we'll call them functions. Meanwhile, highlighted in yellow here, if, else, if, else, if, else, these are kind of starting to ask questions. What might these be called if you have some familiarity? Yeah, it turns out many programming languages, if you've seen any before, would call these conditions. They're branches or proverbial forks in the road. If this is true, go this way. Else, maybe go this other way, or perhaps a third or fourth direction altogether. Meanwhile, if we actually look at these highlighted phrases, if Smith is among names, or if Smith is earlier in book, or Smith is later in book, these are the specific questions we're asking in order to make that decision. These are known as Boolean expressions, named after a gentleman by the last name of Boole some years ago. And so a Boolean expression is just a question that has a yes/no answer, a true/false answer, a 1/0 answer, if you will. And that's a nice mapping to what computers are really good at. So within conditions, you have Boolean expressions to decide which fork in the road you want to go down. And then lastly, highlighted in yellow here, are go back to step 2 in a couple of places. This is inducing some kind of cycle or loop that's telling the computer to do something again and again and again. So in short, we have these building blocks already conceptually. And it turns out we can now start to translate these to an actual programming language. The first of the languages we'll introduce in CS50 is something called Scratch. Turns out this is not a text-based language like in my English pseudocode there, but it's graphical, and things look like puzzle pieces that you can drag and drop, and they interconnect if it makes logical sense to do so. And in fact, some of you might have played with this back in the day as kids, or even more recently, because it's actually targeted typically at students in like after-school programs who just want to learn more methodical, more algorithmic or computational thinking. And we're going to use it to explore not only these building blocks, but a few others as well. It turns out in the other languages we'll explore in CS50 and beyond are languages like C that we'll actually transition to as quickly as next week to then translate what we do this week in Scratch to next week in C. And in languages like Python and JavaScript and SQL, which we'll also explore, do we have other capabilities. The ability to store data in variables, so to speak. To use threads, which means get the computer to do multiple things at once. Events, to mean listen for things happening, like a click on the page or a human typing or even saying something. We'll be able to do all of the things that you take for granted in your very own phones. And we'll do this first by way of this guy. So this is Scratch, the default C.A.T that comes with this programming language from MIT's Media Lab. And via Scratch, can we start programming him to move up, down, left, right, say something, utter something, and other commands altogether. In fact, let me go ahead and switch contexts here to show you the very first thing I ever wrote in Scratch. It was back in the day when I was in graduate school, and Scratch had just been invented by MIT. Let me go ahead and open this. And I called it Oscar time. And if we could perhaps have a volunteer come on up for just a moment. You have to be comfortable being on stage and on the internet. How about here in the white shirt? Saw your hand first. Come on down. So this is Oscar time. It's implemented in a language called Scratch. And at the end of the day, all that is underneath the hood of this program is functions and loops and conditions and a few other of these concepts. Hi, what's your name? Aviva. Aviva, David, nice to meet you. Come on over here. And in just a moment, I'm going to go ahead and click the green flag at the top left-hand corner, which is going to play this game. And we'll see on the screen the instructions.
Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. If you really want want to see something trashy? Look at this. I have here a sneaker that's tattered and worn. It's all full of holes and the laces are torn. A gift from my mother the day I was born. I love it because it's trash. Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. Here's some more rotten stuff. I have here some newspaper, 13 months old.
All right, very good. A round of applause for Aviva for coming on up. Thank you. Here, up, Aviva. A little CS50 stress ball. So, suffice it to say, if you're tired of this song, consider how tired I was 8 hours later while like debugging and building this program. But consider what it is we just saw. It's this interactive game and stuff is animated and music is playing. But if you focus on decomposing, so to speak, this program into just basic building blocks, this is just kind of a big abstraction over some lower level pieces of functionality. Like this trash can here. At the moment, it's just a picture. And on occasion, as soon as Aviva dropped something into the trash, the lid came up and Oscar came out. He said something, and then he went back down. But that animation is super simplistic. It was just a sequence of 1, 2, 3 or so images displaying and then going back down to create the illusion of animation. Meanwhile, every time Oscar said something, that was keeping track of her score in what's called a variable. In algebra, you have x and y and z. But in programming, you have the same idea, but it's generally more useful to call them more descriptively like your score. And so there's probably a variable in this game called score that was just keeping track of how many times Aviva had dropped something into the trash. Meanwhile, the trash itself, and the shoe and the newspaper and even more things happen eventually, were falling from the sky at sort of random locations. And that's because I programmed the game to sort of start the trash here or over here, just to make it a little more challenging as the game picked up. And in fact, things start falling faster and faster over time, like a typical game, getting more and more difficult. So how do we get to something like that? Well, let me go ahead and open up Scratch itself and introduce the environment. So in Scratch, you essentially have 3 general areas. And it's web-based, and so you can do this on any computer. And in the left-hand side here, you have those puzzle pieces to which I referred earlier. These puzzle pieces are all mapping to functions or loops or conditions or variables, things that we saw before. And I'm going to be able to drag and drop them into the middle in order to interconnect them and write my program, which we'll do in just a moment. Meanwhile, Scratch lives in this stage, this world, where you can move up, down, left, right. You can change what Scratch looks like. You can add other characters, otherwise known as sprites, in order to have multiple things happening at once. And of course, you can full screen it. And so the Oscar time game a moment ago was actually a whole bunch of sprites. Oscar's trash can was one. Each piece of trash was another sprite. The newspaper was a sprite, and so forth. So each of them were separate programs running in parallel at the same time. So let's actually make him do something. It turns out that if I jump down to, say, events, I'm going to see one of the most powerful blocks from the get-go, which is this, when green flag clicked. That's indeed how I started the game with Aviva, by clicking just above Scratch's world, this green flag. And if I wanted to stop it as I did, you can click the red stop sign to say stop. Meanwhile, the green flag I can constantly listen for. By dragging and dropping this puzzle piece, when the green flag is clicked, what do I want to do? Well, let me go up to looks. And these are just different categories. And we can scroll through all the different colorful blocks, but they pretty much just do what they say. I'm going to go under looks, where I know there to be a block that's called say. And I'm going to go ahead and type the most canonical computer science thing, hello world, in this box. So notice that functions themselves can actually take inputs. And the input to this function, say, is going to be hello world. If I now go over to the green flag and click it, hello world. All right, so not all that difficult, not all that interesting, but it actually got the job done. And so my program is indeed just this. Well, how might I make this a little more interesting? Just saying hello world all the time isn't all that compelling. Well, you know what? Let me think. Let me undo this. Let me scroll down to sensing, and notice this. Functions can also take input from the human. And functions can hand you back a value, a so-called return value. So this block here, ask something, by default it says what's your name and wait, is another function built into Scratch that allows me to do this. I'm going to go ahead and drag this here. And I'm going to let it say, what's your name? Notice now that below this block is a special block, whatever it is the block returns. So answer is whatever the human's going to type in. And if I want to now save what the human typed in, let me go again to looks. go to say, and notice that these blocks are kind of magnetic. They want to snap together, so I'm going to go ahead and let go there. And if I go back to sensing and grab answer, notice that even though it's not quite the same size, it's going to grow to fill. And now I can have my program ask the user what his or her name is, and then say whatever that answer is. So let me go ahead and stop and click play again. Notice it's asking me for my name, so let me go ahead and type in David, enter. OK, it's a little weird way to greet someone, David. So it'd be nice to clean that up a bit. So you know what? I know this only from having poked around before. Not all of this is obvious at first glance, but it turns out that under operators, the category, there's this thing here, join, apple, and banana, which are just default values. You can change them. Because what do I want to do? I want to say hello, David, or whoever. So I kind of want to say hello, comma, and then David, whatever the human typed in. And that's what join lets you do. It lets you join or concatenate two phrases that are somehow provided by you or the user. So let me pull this out, the answer. Let me go ahead and grab the join block. Notice it, too, is going to grow to fill. Let me go ahead and say hello, comma, space, and now drag answer into there. And notice this nesting, just like in math, this nesting of functions. I can first join hello and answer by taking those two things as input, and then pass them to say as another input, because these things are layered on top. And so now if I stop this and play it again and say David, hello, David, now we have the makings of a more interesting interactive program that isn't just hard-coded. Of course, it's not nearly as audible as something like Oscar time a moment ago. So let me go ahead and do this. Let me start over altogether and treat Scratch like the cat he is, and just start the sound called meow. So it turns out there's a category of blocks called sound. And within sound, there's play some default sounds. So start sound meow. And now things will get a little cuter. Aw. And now if I, again, and I can kind of simulate a cat by standing here for a while and keep clicking this button. But you know what? Let me make him meow a few times, because that's more realistic. So let me grab a second one and a third one, and you get this infinite supply of blocks. Let me hit play. Seems like a bug. Let's try again. Play. This is my first bug or mistake. This looks correct. It says when green flag clicked, start sound meow, start sound meow, start sound meow. Why am I only hearing one meow? Yeah, was it? Yeah, they're kind of at the same time or so close to the same time that the sounds are kind of tripping over each other and just overlapping, right? The block literally says start sound meow. But computers are really fast. If you've heard of the expression like gigahertz, that's a unit of measure. And if your computer has a 1 gigahertz CPU, central processing unit, or brain, that means it can literally do like 1 billion things per second. It can certainly start 3 sounds super fast. And if they're effectively all happening one after the other, before the sound even finishes, you're just hearing one net effect. So how can we fix this? Well, I can actually go and fix this with this block here. Play sound meow until done. Play sound meow until done. Play sound meow until done. And now, OK, it's a little unhappy, this particular cat, but at least it's now more correct. And as it turns out, if I go to control, you know what? There's this block here. Wait some number of seconds. I can go ahead and insert this here. Let me do another one here. And now hit play. Yeah, it's not bad. It's now sounds a little more realistic. But honestly, if I keep doing this, or you can actually right-click or control-click on blocks, duplicate them, and just copy and paste even more if you want them. So if I were to do this, now it's just going to go 6 times. And then I could copy it again and go 12 times. But there's got to be a better way, right? This is now bad programming. This is bad design, because I'm literally copying and pasting, albeit graphically. But we've already seen a building block that with which we can design this program better. It's correct, but it's not well designed. What would the building block be that I need to make this a little cleaner? OK, a for loop don't quite exist in Scratch, but a loop fundamentally do something cyclically. And indeed, if I go under control and start poking around, you'll notice that there's a few blocks that might apply here. There's the repeat block some number of times, or the forever block, both of which sound like loops or cycles. So sure enough, let me go ahead here, and I can throw away blocks by just dragging them to the left. Let me pull this out for a second, and then just say forever, play this sound, and then wait 1 second. So now my program looks like this. we'll never know if it's technically correct because it's just going to go, we think, forever. But it looks like this is correct. And it was a lot less code. And it's a lot easier to maintain because if I want him to kind of get sleepy, I can then maybe say 2 seconds instead. And we can adjust this on the fly as we go. But let's start to combine some of these ideas now and change what it is the ultimate effect is. Let me go ahead and open an example I made in advance. This one's called Count 0. And we'll put this on the website later so that you can play with it if you like. And this is kind of the opposite of counting sheep. Rather than me or this person sleeping counting sheep, this sheep will count itself. So let me go ahead and just play. And adorably, he seems to just be counting 1, 2, 3. But why is that? He's just going to count forever. But let's look at the blocks with which he's counting forever. When green flag clicked, set counter. Turns out this orange block is what we called a variable. So in algebra, it'd be like x or y or z. Those are not descriptive. I called this one counter instead. But I could have called it x or y or z. And then I forever say the counter for 1 second. Then wait 1 second. And then change the counter by 1, which technically means just increment it. Add 1 to it. And the sheep is just going to, therefore, count up and up and up. Now, this is a little tedious, but that's kind of the point of counting sheep, of course, to fall asleep. But what if this sheep actually kind of liked counting a little faster? Well, let me go into operators here. Multiplication sounds like it could get us places quicker. And let me go ahead and go to variables. And instead of changing the counter by 1, let me go ahead and just keep setting it to something else. So let me drag and drop this. Set the counter equal to something times something. Specifically, the counter times 2, thereby doubling, 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 doubling. That would seem to grow, so to speak, a lot faster. Let's see. 1, 2, 4, 8. So he's counting faster, but it's still kind of tedious. What if we instead do this? Let's stop waiting. And let's go ahead and, with looks, not say counter for 1 second, but let's just quickly say counter. So I'm going to say the counter. Whoops. I'm going to say the counter, and then I'm going to set it to itself times 2. So here's where we're at. Initialize or set the counter to 1 initially, say it, then double it, then double it, then double it, saying it along the way. So here we go. That's impressive. So now the sheep has counted up to 10 to the 60th so far. 10 to the 100th. OK, now it doesn't even fit in the speech bubble. But he's still going. How high can he go? What's the biggest number you can count to in a computer? Anyone want to guess? Could be here a while. 10 to the 270th now? How high can you count? Or rather, OK, so we gave up and just called it infinity. So it turns out infinity does have a precise value, 10 to the 250th or so. But what happens here? Well, because computers at the end of the day are just storing information digitally, but that information digitally has to be physically stored using electricity, using these lower level switches called transistors. At the end of the day, my phone, my laptop, whatever device in question only has a finite amount of those things. I only have a finite number of fingers. Using unary, my old school hash mark approach, I can count to 5 on this hand. Using binary, I claimed I could count to 31 on this hand, but it's still finite. I cannot count to infinity on this hand because I only have 5 fingers. Similarly, does a computer only have so many transistors or so many bytes or bits of memory? And at some point, the programmer has to think about what is he or she going to do when the user wants to count so high that you can't physically fit it anymore. You have to give up like this and say something semi-accurately, or you have to handle the issue in some other way. And we'll see when we get to C that how you handle this problem is not necessarily straightforward. And indeed, a lot of software out there does not handle this problem. And odds are all of us have programs that if you type big enough words or big enough numbers into them, they might very well break or crash or freeze because the humans, unlike MIT, did not anticipate that might actually happen and handle it. Well, let me go ahead and do this. Let me open up this program and see if we can't read the code now. This is called pet0. And this is a program that simulates petting. So if I click play and don't touch the keyboard, nothing seems to be happening. But if I now move my cursor over to the cat, oh, it's kind of cute. Right now it's more only meowing on demand when you pet the cat. Why? Well, notice I've added some other building blocks. We haven't used this one before, but it intuitively probably makes pretty clear sense. When the green flag is clicked, forever do the following. If the cat is touching the mouse pointer. This thing in blue is what we called earlier a Boolean expression. It has a yes, no, a true, false, a 1, 0 answer. And touching mouse pointer is one of the options in the little drop down here if you tinker with it. So if the cat is touching the mouse pointer, then and only then play sound meow until done. So we've combined now functions with loops with a condition. But why the loop? The cat's only meowing once when I pet him. Why am I doing anything forever here? Someone, yeah. Yeah, I might want to pet it again, so I want the program to anticipate that. And honestly, if I omitted this forever block and my program instead looked just like this, so let me get rid of that and this, and then I clicked play, and now I hover over him, why is it not working even once? Say again? Yeah, so I mean, at this point, if I can summarize, it's that happened. The computer's so damn fast that this already happened by the time I moved my cursor over to the cat. And at the moment I clicked play, I was not touching the cat. Those blocks executed, so to speak, top to bottom. That's it for the program. So by the time I move the cursor over to the cat, the program is over. It's not listening. And so forever, this way I can actually listen in perpetuity for something to actually happen. What if I want to do something not just if something is true, but handle two cases, if or else? Well, let me go ahead and open up pet1. And this is another example. And could someone perhaps describe, after reading this code, what this program is going to do instead? Yeah. Exactly. And let me summarize more verbally. So if this time you're touching the cat, it's going to roar instead. Else, it's just going to meow sweetly. So this time it is meowing perpetually, once every second. But if you touch this particular cat, he doesn't like it. So play meow, meow, and now don't touch the cat. So now we might interact in two different ways by having two different roads that you can go down. Well, let's actually make something a little more interactive. Let me go ahead and open another example, this one called bounce 0, because now we can start to see some design elements from what Oscar time was. Like this now is getting a little interesting. What is actually going on here? So let me zoom in on the blocks here. This block is just saying forever, move 10 steps, which is another block we haven't seen. But 10 steps is like 10 pixels, so move 10 pixels on the screen. But if you're touching the edge, then turn around 180 degrees. And you can see exactly that happening. Scratch is turning around 180 degrees. And this rotation style just means double back. Don't like loop around 180 degrees. So that's kind of cool. But this is not how humans or cats walk. Like, what is obviously unnatural about this? Yeah, I mean, I can't even simulate it, right? Like his feet are in static position, and yet sliding back and forth on the screen. And yet that is not what walking is. Like walking presumably has some kind of movement. And what? Well, we could just kind of simulate it like, OK, I could just walk. Walking. And you can imagine taking like really quick photographs of my legs or the cat's leg moving, and then just deciding this photo will be representative of one step, this photo will be representative of another. And you know, with just two of those steps, I'd wager we could actually do a pretty good job of simulating what walking looks like. In fact, if I go back to where we began, this picture of Scratch, what if I just move his legs ever so slightly? Then go back, then go forward. And even just in my PDF, I can simulate animation by hitting up arrow, down arrow, because it kind of looks like he's walking now, when really your human eyes are just seeing two different pictures again and again. So how can I do this? Well, if I go back to Scratch, he's still walking. Let me go ahead and open up bounce 1, the second version of this, and now do this. OK. So how did I add this? There's a little purple block that we haven't seen yet, but if you poke around the categories, you'll see other blocks like this. Next costume, that just keeps changing the costume that he's wearing. It turns out Scratch exists as a picture, and his default picture is him not moving. But if I go up here to top left and click costumes, you can actually see that here's his one costume, here's his second costume. And so that purple block that says next costume, because it's in the forever loop, it just keeps doing next, 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 just showing one costume or the other. They're clearly mimicking walking. Now, this is not very natural. Why don't we slow him down to, say, 5 steps at a time and have him go again? No, this is still going pretty fast. Let me go ahead and say we could have we could have him wait a second after moving very dramatically. We should probably speed this up. So let's wait 1/10 of a second, 0.1. Or maybe that's even, let's do 0.01, 100th of a second. Now it's getting a little more realistic. But this is what animation is. If you've ever watched a cartoon or a movie based on pictures like this, you're just tinkering with some of these parameters, these inputs, in order to produce this output by understanding what the fundamental representation of these things is, which in this case are just pictures, again and again and again, in order to create that animation. But what about interactivity? Let me do this one myself. Let me go ahead and get rid of this, go back to events, and say when green flag clicked. Then let me go ahead and grab a forever block so that this keeps going again and again. And then let me go ahead to go to motion. It turns out that under motion, there's this block we haven't seen, point towards the mouse pointer. And let me go ahead and pull this in here. And then let me have it move just like 1 step at a time instead of 10. What is this going to do? What's this program do? Yeah, say again? Follow the mouse. Yeah, this is kind of like a way of taking your cat for a walk. Perhaps not quite the animal we intended, but he'll follow the cursor. And I can actually speed this up a little bit. So let's have him move 10 steps. OK, now, there we go. So now he's moving up and down. And so now it's interactive. So you might recall that when we were playing Oscar Time earlier and picking up the OK, don't do that. See, that's a bug. He's just confused. He's constantly moving toward it, but you're already OK, so we're going to stop. OK, so now he's following. But that's how we might now create, for instance, the ability to move those pieces of trash around and have them follow the mouse cursor. If you think back to Oscar Time, every time you picked up a piece of trash, it followed the cursor because there was a forever loop and a block like this pointing toward the mouse pointer. Well, now let's integrate multiple ideas and actually have multiple scripts. I proposed earlier that programs can actually have multiple threads. A thread is just a fancy way of saying, in our context, multiple scripts in one program that are happening essentially in parallel. A computer can effectively do multiple things at a time thanks to threading, and more on that down the road. So these are more involved, but let's see if we can, let's understand first what this program does. Let me go ahead and hit play, and this one tends to be a little loud. So the sea lion is just barking endlessly, annoyingly. So by reading the code, how can I stop him from barking? Hit the space bar. All right, so hit the space bar. OK. I could just stop the program, obviously, but this program's still running technically. But why did that work? Well, notice this on the left-hand side is the first script. When the green flag is clicked, set this variable that I called muted to false. Could have called it x or y or z or counter, but none of those really make sense, so I called it muted. And I set it equal to false, which is, again, a Boolean value. True or false just mean yes or no. Forever, if the key space is pressed, then do this. If muted is currently false, then change muted to true. Else, change muted to false. So if muted is false, change it to true. If muted is true, change it to false. Anytime the human hits the space bar, update that variable. Now if we look at the other script, which is also driving the sea lion, what is he doing? Forever, if muted is false, so if he's not muted, if muted is false means not muted, start the sound sea lion and then think hi, hi, hi for 2 seconds, and then wait for 1 more second. And then just repeat, repeat, repeat. But if I change with the spacebar muted to true, he's going to say if muted equals false, that's not so. I'm not going to play a sound this time. And so now we have the ability to integrate multiple scripts together in order to achieve a more interactive result. And what about this? Back in when I was a kid, might have played over in the summers like Marco Polo. Super simple game where we played it in the pool for some reason, where one person in the pool very safely is blindfolded, and then he or she yells Marco, and then everyone around him or her is supposed to yell Polo, and then the person who's blindfolded is supposed to go chase the other kids in the pool and tag them, and then they become it. But in other words, it's this like signaling mechanism. Someone yells Marco, and everyone else responds to that broadcast of the word Marco. Well, it turns out we can simulate this with these two puppets. This guy here, notice that I've highlighted the orange puppet because there's a second blue puppet there, separate sprites, and these are just photographs we uploaded to the game. Forever if the key space is pressed. So if the space bar is pressed, say Marco for 2 seconds, and then broadcast an event. Meanwhile, the blue puppet here has a super simple block, but it's fundamentally different from the ones we've seen. He's not starting when the green flag is clicked. He is starting only when he receives an event. So it turns out that sprites in Scratch can't hear or see what the other one is saying in those speech bubbles. You have to use a fancier technique, which is this special block called broadcast, which is like passing a note digitally from one sprite to another that the other one can read or receive, so to speak. So only when he receives this event, so to speak, does he say polo for 2 seconds. And again, the orange puppet sends that secret message just using this other puzzle piece, broadcast an event, like passing a note that the human doesn't actually see. So if I now hit the green flag and hit the space bar, orange yells Marco, blue guy yells polo in response, but those aren't timed together. Rather, the blue guy is hearing what the orange one has said, thereby allowing multiple sprites to actually intercommunicate. So how did we get here? Well, recall that we had all of these building blocks a moment ago. First, we started out with just functions and conditions and Boolean expressions and loops. We've now added to that the ability to store information in variables and threads to do multiple things at once. And then if you do have multiple things happening, events where they can intercommunicate somehow. Yet another building block. So if we now take a step back and consider how we can make functions of our own, we have the final piece of the puzzle, so to speak. Let me go ahead and do this. Let me go ahead and create a simple program with when green flag clicked that simply simulates coughing for a cat. So this cat is going to say not hello, but cough for 1 second. And then he's going to go ahead and wait for 1 second. And then I'm going to go ahead and copy paste as I did before. This is one of those do as I say, not as I do, to implement this program here where he coughs 3 times. We already know, though, from earlier that this is not good design. Why? You're repeating yourself. Don't repeat yourself. DRY is an acronym, actually. Don't repeat yourself because you're doing 3 times as many times that something that you only really need to do once. The solution before, of course, was just use a loop of some sort. So let me actually take that out. Let me use a repeat block, change 10 to 3, and then just use 2 of these blocks. And notice already, the program's so much more compact. And now, if I want to change the 3 to a 30 or to a 10 or any number, I just change one simple value. I don't have to rewrite or copy paste or delete things. I can update the program much more readily. And now, the same thing is going to happen with just cough, cough, cough. But it turns out that it would be nice to henceforth abstract away from this, right? I just want any program I write to know how to cough. And coughing is really just saying something, perhaps some number of times. But it turns out we can abstract this away in code. Let me go down to my blocks here. And this allows me to click this button, make a block. It allows me to make my own function. I get this dialog window here. And I'm just going to call this block cough. I'm going to go ahead and click OK. And now I have this new pink block that itself can have blocks underneath it. And you know what I'm going to do? I'm going to go ahead and do this. I'm going to go ahead and say cough under there. And now notice on the left, I now have access to this new pink piece. I can now put this in here. So now notice, even though, yes, this is how coughing is implemented on the left-hand side here, next time when I write a program, I just want to call cough. And I don't care about those lower-level implementation details. I don't care about the binary or any of that. I just want this to be an abstraction. But I could do better than this. Wouldn't it be nice if instead of just repeating cough 3 times, what if I made that a feature of cough? So let me do this. I can go ahead and right-click on this pink piece, and I can edit it. That brings up that same window from before. And notice this, add an input. So when I make a custom block, I can actually make pretty fancy blocks just like the ones MIT gives us with the software. And now I can type in something like n. And if I add a label, just to make it more descriptive, I can just say times. So now I've made a special custom puzzle piece that says cough some number of times, where n for number is just the go-to variable that programmers tend to use. So now I can actually move this repeat block into cough itself. But rather than hard code 3, notice this. I can steal that variable and now say cough this many times by repeating, saying this again and again and again. And now, when I cough in my actual program, I just type in 3 here. So I have this beautiful abstraction now, so to speak, cough this many times, and I, and no one else in the world, never again needs to care about what it means to cough because we've already implemented that before. And so just as MIT has given us so much functionality that we ourselves don't have to think about, so can I now make functionality that I don't have to think about. And as we progress to higher level languages like C and JavaScript and Python, we're going to continue this process, sometimes solving problems ourselves by making our own custom puzzle pieces, but very often using things called libraries, code that other humans wrote before us that's just useful to get the job done, just as Scratch has done here in part for us. Let me go ahead then and bring all of this together by opening this other example here. Let me go ahead and open up this one, which isn't something we've seen, but it's kind of an interactive game like this, made by a former student. Should we have an apple? Yes? Little animation. OK, that didn't end well. Let's try again. Play again. And notice the say block is happening. There's some kind of ask block. The student was checking if the human typed in yes or no. Let's type no this time. No apple. Ooh, cupcake. OK, yes. Enter. OK, don't do that. One more life. Here we go. OK, no apple. No cupcake. Oh, a little variable counting that. OK, so I won the game. In our final moments here, let me go ahead and open one final example. As you know, CS50 is offered not only at Harvard, but at Yale as well. So it seems fitting to perhaps end on a note that pits one campus perhaps against the other by way of another game that a former student wrote called Ivy's Hardest Game. But for this, I think we need one final volunteer who's coming up. OK, first hand, right there. Come on down. So in Ivy's Hardest Game, it's a game played with the keyboard. And even though it might look a little overwhelming at first glance, just like Oscar Time did, and heck, just like the gingerbread animation might, realize that if you decompose it in just your mind's eye, thinking about what those individual building blocks are, you can probably guess what the puzzle pieces are. Hi, what's your name?
Hi, I'm Andrea.
Andrea, David, nice to meet you. Here is Ivy's Hardest Game. We'll pitch you against all of the Ivies here. And then right after this, we adjourn for cupcakes in the transept. Ready?
You can't touch this. You can't touch this. You can't touch this.
Nice.
You can't touch this. My music hits me so hard, makes me say, oh my Lord, thank you for blessing me. What am I to rhyme and too hype? It's just good when you know you're down. A super dope homeboy from the Oak Town, and I'm known as such. And this is a beat up you can't touch. I told you, homeboy, you can't touch this. Yeah, that's how we living, and you know you can't touch this. Look in my eyes, man, you can't touch this. What's the show here? Fresh new kicks and bands, you got it like that. Now you know you want to be so move out of your seat and get a fire girl and catch this beat while it's rolling. Hold on, hold a little bit, let them know what's going on like that, like that. Hold a little bit, just fall on back, let them know that you're too much. And this is a beat up they can't touch. Can't touch this. While we standing there, man, you can't touch this. Yo, sound the bell, school is in, sucker. You can't touch this. Give me a sound, rhythm, make them sweat. That's what I'm giving them now. They know. You talk about the hammer, you talk about a show that's hot and tight. Singles are sweating so fast in the whiteboard tape. To learn what's gonna take in the night to burn the charts.
Second to last level.
You work hard or you might as well quit. That's word, because you know you can't touch this. You can't touch this. Break it down. Stop. Hammer time. Go with the flow.
Come on.
And it's steady.
Do it.
You probably already tried. Your hands in the air. Bust a few moves. Run your fingers through your hair. This is it.
answer choice for? No, it's okay. One more left.
Stop. Have time.
All right, a round of applause for Andrea if we could. That's it for CS50. See the website for details. We'll see you for cake in the transept.